So let's move on to the next talk. Okay, next speaker is Georgios Vacalis, and he's going to talk about detection of high-frequency gravitational waves with high-energy pulse lasers.
The center, it's better calibrated.
Okay, so this is okay. So to go
On the top is the pointer, and that's just back and forth.
Okay, great, thank you. Okay, so can you hear me? No, great. So I would like to thank the organizers very much for for organizing this event and giving me the opportunity to present a subject that was introduced by my supervisor Gianluca a bit earlier today. So I will talk a little more about the detection of high-frequency gravitational waves and detection mechanism, which is based on using high-energy lasers. So as we all know, so gravitational waves, they were predicted over a century ago in the general theory of relativity, but they were detected only a few years ago. And, well, LIGO and Virgo, the collaborations which made these detections, have a sensitivity up to a few kilohertz. But as we saw quite a lot during this seminar, is that higher frequencies are very much of interest because they are often associated with new physics. So when talking about lasers, the detection mechanism is based on the graviton to photon conversion, so the inverse Gertsenshtein effect, which Gianluca mentioned a little bit, but I will talk a little bit more about it. So for this short presentation, I will just give some motivations, which may not be necessary in a conference like that because everyone is really motivated. Then I will talk about the conversion itself with the lasers, how it translates into sensitivities using different lasers, and finally talk a little bit about the sources of high-frequency gravitational waves to which we might be sensitive or not. So first about the motivation. So as we all know, there are two main sources of gravitational waves. So one that is more cosmological and other category, which is the astrophysical. So here I just show one plot from this paper about the evaporation of primordial black holes in the early universe. So we're talking about black holes that evaporated before the BBN. And what the authors showed in this paper is that the spectra here have peaks that are all above terahertz, which motivates a lot the search for gravitational waves if we are interested into cosmological sources. In the other category, we have the well-known system of black hole mergers. But in this case, if we are interested in mergers, we have to remember that the highest frequency that is emitted by a merger, at the, which is the ISCO frequency, scales as the inverse of the total mass of the binary. So looking at high-frequency gravitational waves automatically means if we are interested about mergers, also looking for very light binaries. So, of course, this becomes challenging because at the ISCO frequency, the strain of a gravitational wave is proportional to the total mass. So, talking about the conversion itself, so that's a very simplified picture that Gianluca showed previously. So, to remind everyone, we have an incoming laser beam that is counterpropagating with respect to an incoming gravitational wave. They interact, and through the inverse Gertsenshtein effect, we generate a signal where here we assume that the frequency of the monochromatic gravitational wave is bigger than the frequency of the laser. And then we just assume that there is a detector here measuring the signal, that we'll just assume it is an abstract object. Moving on to some formalism. So I realized today that there is apparently a lot of debate about these Maxwell equations in Kerr space. I didn't realize this was the case, but of course we can talk about the validity. But the idea is that we consider a metric perturbation on flat space that we insert then into the Maxwell equation in Kerr space. So varying with respect to the the photon field, we have the equations of motion, where here what I highlighted in blue is the contribution coming from the gravitational wave, whereas the red terms are the ones coming from the electromagnetic components of the laser. So the idea is to solve the Maxwell equations and then compute the total energy that is emitted by, let's say, integrating over a pulse length the power, which is just given by the Poynting vector. And then if we are able to, if we can assume single photon counting, assume that this power should be at least the energy of one photon. So the results that I'll discuss briefly is what we realize is that there is resonance occurring in the case of this system, where in the case where we don't really know what the frequency of the gravitational wave is, we have the energy of the signal going into the detector scales as the laser energy times order h squared. But if we choose the gravitational wave frequency to be twice the laser frequency, what we have here is that we have an enhancement of a factor of L omega squared, where L is the length of the interaction region. You can think of it as the pulse. And for the laser systems that we are considering, this is, we assume it is a large number. So the sensitivity then, we can find it by assuming that this energy has to be bigger than the energy of one photon. Yes?
Can I ask a question? So you are considering only one pulse, or you are considering multi-pulses in this case? Because
so okay, so the previous picture, in the previous picture it was one pulse, but yes, we generalize it to multiple pulses. So this is what this here ns. So that's the number of shots. So we assume that you can have a number ns shots, and then you can, let's say, increase the sensitivity of your detector. See it, yeah.
Okay, thank you.
So, talking now about the sensitivity. So we had a general formula for a laser beam, and then what we have here is, so what I do is I just plot the parameter space. So while not showing, of course, all the detectors like CAST, Oscar, etc., just because they happen around the same frequency, and just wanted to show the sensitivity of the lasers, but of course they are present. So we have put in the numbers for three different lasers. So the terahertz free electron laser, the NIF, and the X-ray. So operating at three different ranges of frequencies. So what you see here in the three red peaks, so this shows actually that the NIF operates at fixed frequencies. So since we have that resonance occurring for a precise frequency, we have that the sensitivity is bigger when the frequency is matched. And then the three black lines that continue below are just projections on a NIF-type laser. If we increased the rate of the shots, that would give more energy during the duration of the experiment. that would increase a little bit the sensitivity. So there was a question at Gianluca's presentation about what this brown line is. So this is, well, going a bit forward. When we think about the possible sources, one source of interest is, of course, the black hole mergers. And what I plotted here is mainly the fact that if we have, I wanted to compare the, if we are sensitive to black hole mergers that are located between 1 parsec and 1 kiloparsec away from us. So we see that even though the distance is not very big for cosmological scales, we still, with today's lasers, are not near it. So now talking a little bit about the sources. So I didn't mention it, but of course our sensitivity is way below the BBN bound. So to explain, so I'm assuming almost everyone knows what the BBN bound is, but just to remind you, it is the fact that the BBN predicts correctly the abundance of light elements in the universe when the energy density is assumed to be to contain photons and neutrinos, and the correct predictions are there if we have if any extra sources of energy density is equal to 0. So because of the good predictions, if we want to add the energy in the forms of gravitational waves, then they should let's say extra energy should be small enough in order not to spoil the predictions. So what this translates into is that for an optical so for optical frequencies of gravitational waves, we see that the strains should be below 10 to the minus 36. Yes.
Qualify, of course, this is valid as long as those stochastic backgrounds are produced before Big Bang nuclear synthesis.
Exactly.
You could generate these much
yes.
later, no problem.
Yes, thank you for adding that. Indeed. So, of course, this is an upper bound. So any sources that that could emit in this range could be even much lower. So, of course, as it was expected, the BBN is of any let's say gravitational waves coming from cosmological sources are out of reach for today's lasers. So what about now looking at astrophysical sources like black hole binaries? So the idea here is that we could say if our system is close enough, we could detect something. But what we should be careful about is the fact that for a black hole merger, the frequency is not constant over time. So it is almost constant in the early stages of the merger, in the in-spiral stage. But as we get closer to the merger, then we have change in frequency. But for our system, we saw that we are sensitive when the frequency of the gravitational wave is twice the laser frequency. So if we want to estimate the validity of our supposition, we find that actually any shift from the resonant frequency divided by the frequency itself should be lower than this quantity here. That itself is much smaller than 1 in the systems we are considering. So translating that into the duration over which our change in frequency should not be very big, we find that the duration of our experiment should not be should be smaller than this quantity here. And in our calculations, I forgot to mention this, but I'll say it now, we assume that the duration of the experiment was 1 day. So if we want, for example, our duration to be of the order of days, so I've just here as an illustration plugged in the numbers for a terahertz laser, and we see that the total mass of the binary, well, it is extremely small. So not very promising, unfortunately. To conclude, so what we saw is that lasers are possible ways to explore gravitational waves in the universe when they are when we have when there are of high frequency, so between a few tens of terahertz up to the X-ray regime, and in the resonant case we find that the sensitivity grows as the square root of the frequency. So as also it was expected, we found that no cosmological sources can be detected because the BBN bound is very strong. So then we focused on looking at black hole mergers, which could be close. But unfortunately, we find that if we want the duration of the experiment to be more or less reasonable, we have to assume that the black holes have to be even smaller, which makes the detection even harder. So having said that, I would also like to point out that the results can be found on a paper on arXiv. And having said that, I would like to thank you for your attention, and I'm happy to answer any questions.
Okay, thank you for that.